Good morning. Welcome to today's presentation on selecting the right hose for your fluid system, brought to you by Swagelok Northern California. I'm your host, Rebecca Donaldson, and I'm joined today by Patrick Werrlein of Swagelok. Patrick will discuss hose terms and components, how application variables influence hose selection, 5 steps to selecting the right hose, and applying those 5 steps in an example. Patrick Werrlein joined Swagelok in April 2008, bringing with him 16+ years of experience in the hose industry. Before that, he was principal of Coreflex LLC, the hose manufacturer that Swagelok acquired. It looks like we have pros on the line from a variety of industries: semiconductor, energy, biopharm, and food, beverage, dairy, among others. Some of you are probably designing hoses for very niche applications, and others may be looking for a very general overview. To everyone on the line, please put any questions you have into the Q&A box, and Patrick will try to answer at the end. We are recording this session and posting it at our website, like with other webinars. Let's get started with Patrick's presentation, selecting the right hose for your fluid system. Patrick?
Thank you, Rebecca. Good morning, and thank you for attending today's session. I'd like to begin with where the true opportunity starts, recognizing the need for improvement. Hoses are often overlooked as it relates to the overall operation. However, the consequences of the failure can be tremendous. Now, thinking about some of those consequences, downtime. So if a hose failure, if we had a critical application and we had downtime because of a ruptured hose, that becomes very costly to us. Think about wasted products. Some of our applications require us to transfer media that has high cost. Environmental damages, so we could have EPA issues. Or even worse, we could have where personnel get hurt. So let's look at an analogy of car tires as it relates to hose life and maintenance. Its life depends on driving conditions, your style, miles traveled, all play a role in the life of that tire. Proper maintenance, however, can prolong the life. Rotation, proper pressure. However, we know for sure that that tire is wearing down. And so it's a very similar situation with hoses. So we have to start with first understanding that the fact that these components are wear parts. So what I'd like to do now is, before we get into selecting the right hose, I think it's important to understand the nomenclature. So let's walk through a couple of these. First off, hose is a flexible conduit consisting of a reinforced tube. If the hose did not have any reinforcements, it would be considered flexible tubing. Third, bend radius is a measurement in which a hose can be bent. Minimum bend radius is the measurement prior to the deformation of the tube, which then jeopardizes the integrity of the hose. This is the guidelines used in selecting and designing the hose. Force to bend is the amount of force, usually measured in pounds, needed to achieve the bend radius. As mentioned, you can see from the illustrations to the left, the hose can make a bend with a 12-inch measurement, which means this hose would go to market with a 6-inch bend radius. This helps when selecting a hose or designing a system. Another characteristic, however, that is extremely important is the force to bend. A hose with too much force to bend jeopardizes the life of the performance of the hose and puts additional stress on the connective equipment. This is something that's hard to categorize or to list in a catalog, but actually has great value. And so, you know, what I like to do is use another analogy, and you think about an automobile. In an automobile, when we think about how fast that car is, we typically, you'll look in the catalog and you can see 0 to 60. That's a measurement of speed. But however, you know, you also have to take into account how the car handles. And so when looking at the bend characteristics of a hose, bend radius would be 0 to 60, and the force to bend would be how the car handles. So it's something when we're designing a system or selecting a hose, we're really got to better understand what the force to bend looks like. It's, again, hard to see that from a catalog. It would be something that would be beneficial to have samples. And when you're thinking about using a product, bend the hose to understand what type of flexibility characteristics it has. Now, expanding on that, hoses that are overbent will then kink. Now, this is the point where the reinforced tube collapses. This disrupts the system flow and also jeopardizes the integrity of the product, which then could cause a catastrophic failure. So some common causes of kinking would be misinstallation or improper routing, or bending against the natural curvature of the hose. It would be very similar if you think about a garden hose that wants to bend in one direction. When you go to bend it against it, it has a tendency to collapse or kink on you. Well, the luxury of a garden hose is that it would bounce back. However, if we're working with a hose that has any stainless steel braid reinforcements or a plastic like Teflon, it may not bounce back, and again, the integrity of the hose has been jeopardized. So understanding what are the natural curvatures of a hose. You also could have where you have a movement that's too much with the hose, and then again giving you a kink, or just abuse. It could be forklifts or mobile carts going around that could crush the hose. Kinking is also one of the easiest things to overcome with understanding proper routing. The illustration above represents the most common misinstallation, as there's too much stress being created near the end connection. This stress then could jeopardize the integrity of the hose immediately or over a period of time. An easy solution would be to add an adapter fitting to alleviate this stress, as you can see on the left-hand side. And again, just to go back to my garden hose analogy, think about the spigot for your garden hoses. The spigots typically come off either right down to the ground, or they come out on a 45-degree angle. The purpose of that is to alleviate that stress that would be built up if it came right out. Additionally, you notice on most hoses they have a bend protector near that transition from the fitting to the hose. That's also to help in these types of installations. So continue on with nomenclature. Let's just think about flexibility now. Is the overall ability of the hose to flex or to bend? Again, factoring in the bend radius and the force to bend. Burst pressure. Burst pressure is the point at which a hose will fail. Either the hose itself will rupture, or the end connections could be the weak link in terms of pressure containment. Burst pressure is usually it's done in a controlled environment in a lab. We do that to understand what the catalog rating or industry rating should be on the hose. General rule of thumb is a 4-to-1. So in other words, if a lab-controlled environment, if a hose was to burst at 10,000 psi, it would go to market with a 2,500 psi working pressure. Now, static dissipation. Certain medias can cause a static electricity to build up. So if that happens, you have to have a static dissipative core tube that will take any charges that are built up within inside of the hose. They'll allow them to leave or dissipate the other end, and we're going to get into that in more detail in a little bit. Conductivity. A conductivity is a measure of how well a material accommodates the transfer of an electrical charge. So this is a little bit different versus media concerns, where so for static dissipation could be kerosene, where there's a concern that you could have an explosion with the material. Conductivity would be more of if we had a cherry picker where we're working around electrical wires, and we were concerned that if we were brush up against a wire, that electrical charge would transfer through the hose. That would be a conductive hose would allow that charge to transfer. Non-conductive would not. Lastly, permeation. Permeation is how much gas or liquid will move through the hose or escape. This is something you really want to think about when you're specifying a product, depending on what type of gas we're working with. And again, we'll get into that in a little bit more detail. Ordering length is also very important when you're selecting a hose. The wrong length of product could be difficult to install, or it may jeopardize the integrity of the product. Hoses are typically ordered in overall length. However, this means that the flexible portion of the product would have to deduct the end connection. So in other words, if you ordered a hose that was overall length 2 feet, you may only be working with 18 inches of actual flex hose. So you have to take that into account when you're selecting a hose. You can order products if live length is a requirement, so the actual amount of flexibility, the hose length, you'd want to make sure you specify that during the ordering process, identifying that you're interested in live length. So there are a number of application variables and hose options available. So now that we have quickly gone through the hose basics, let's look at how we can properly select a hose for various application types. So some basic application variables are temperature. So with temperature, what temperatures could come in contact with the constructions of the hose, taking into account core tube or any of the layers? And what impact is that going to have over a period of time? For instance, if we were looking at a steam line and you were using some grades of rubber, may not have short-term impact. Rubber may be compatible with it, but what type of life are you going to get? Is there a better alternative material that you could use? Pressure. What pressures will the hose be able to meet? And if not the hose, what about the end connections? We have to look at the overall assembly. Flow. It's also important when you look at designing a system, what is the smallest orifice or opening of a hose assembly? So if you're working with a hose that has it's a half-inch hose, what is the true inside diameter or minimal diameter of that product? Because that's how you're going to get your flow measurements. Chemical compatibility. What is the media and how is it going to impact both the hose and end connections? Drainability. How important is it for you to have the product drainable? Are you a pharmaceutical type application where if you have any product holdup, that could be the potential for contamination? And then lastly, movement. Is it a dynamic application or static application? In other words, will this hose see continuous movement? Is this a robotic arm, or is it going to be installed in one orientation and then continue to be there? Let's walk through the main components of a hose and see how it relates to proper hose selection. These components are the core tube, reinforcement layers, covers, end connections, and then options. First component to consider is the core. The core is the core is also called the inner core, or referenced as the wetted surface. The purpose of this component is to provide media containment. The core tube by itself has minimal pressure ratings. It is not that flexible. It's called the wetted surface because it's what comes in contact with your media. Okay. Now, selecting the right hose starts with thinking about the compatibility, temperature ranges, levels of permeation. Again, what gases, what's the gas and what impact is it going to have? And then cleaning requirements. So for what I mean cleaning requirements, how is the hose itself going to react to any of the possible cleaning agents you're going through? Or is the core tube going to have extractables or leachables? So in other words, if we were a pharmaceutical account and we're going to use, cleanability is really important in our media. If we were using a rubber or a silicone product that's going to have leachables or extractables, that's something we have to think about. Is there a better alternative to select? So, looking at the hose product offerings, there are a number of different materials, but I think we could break it down into four main categories. Starting with metal. Metal has a very wide temperature range, negative 350 F to positive 850 F. It's very good for gas type applications. So if you have a highly permeable gas, metal has a better output in terms of maintaining those gases within the hose. Now, a negative with a metal hose would be the fact that flex fatigue. And a simple way to explain that would be if you were to take an aluminum can and bend it back and forth, over a period of time, that can is going to break in half. That's flex fatigue. Now, PTFE, PFA, those are your Teflons. They have wonderful chemical compatibility. They're very good with pharmaceutical or sanitary type accounts because of their cleanability. What I mean by that is the fact that they have very low absorption. So they have a very low amount of material coming into the core tube. As a result, it has very low extractables or leachables. And contrary to metal, Teflon has a very good flex life. So again, if you were on a piece of robotic equipment where it's a dynamic application, Teflon does exceptionally well. The third category is silicone, silicone being a rubber. Silicone's great in terms of flexibility, being that it's a rubber. Some of the downsides with silicone is the fact that it's chemical compatibility. It's not very chemically compatible, and it also has a relatively high absorption rate, which in turn gives it a higher extractable rate. So cleanability could be an issue. And the last grouping would be nylon. Nylon thermoplastic type products. These are more of all-purpose, general-purpose type hydraulic applications. They're typically a little bit higher pressure. Higher pressure could be 5,000 to 6,000 psi. They do have compatibility limitations and temperature limitations. So now that we've gone through the different types of core tubes, let's look at the different designs. And I think a really nice, easy comparison would be drinking straws. When you think about a flexible drinking straw, there's the smooth part and there's the convoluted part. So let's first take a look at the smooth part. In the smooth area, as it relates to a hose, they're less flexible because of the design. As a result, they're prone to kinking. All metal hoses would have a convoluted type design because if they didn't, they would be rigid stainless steel tubing or metal tubing. The benefits, however, of a smooth bore, it gives you more control in your flow, and it also promotes better drainability. To go back to the pharmaceutical example, pharmaceuticals typically like smooth bores because of the vaccines or whatever they're conveying through the hoses. They know that it's 100% cleanable. Now, let's now look at the convoluted section of that straw. The convolutions allow the material to expand and contract. So as this hose or the straw is bending, at the top of the bend, the straw will flatten out or the hose will flatten out, and at the bottom it will contract. This promotes flexibility. Flexibility even in larger sizes. Larger sizes would be any hose that's 1 inch or larger. A smooth bore, difficulty in flexibility. That's where you would typically go to a convoluted type design. And then within the convolutions, there's a helical and an annular. A helical convolution is it's a continuous convolution. It's very similar to a thread, versus an annular convolution. It's one convolution, it terminates, then another convolution starts. We talked about permeation in the previous slide. Now let's go a little bit deeper. Let's use an example of a balloon. If we were planning a birthday party for a kid and we purchased the balloons, maybe we purchased the balloons too early. What would happen? Well, the balloons may find themselves on the floor the day of the party. So as the party's starting, the balloons are on the floor, and no one's happy about that. Well, the reason that happens is the helium is a really small gas molecule, as is hydrogen. So those small gas molecules will find their way through the balloon. So if the balloon's a rubber or some sort of mylar material, over a period of time, those gas molecules escape, and then as one does, another one follows behind it, and so forth and so on. The same thing happens with hoses. So, for instance, if we were looking at a Teflon hose being a plastic, it's highly permeable. So as you can see from the picture here, these would be the gas molecules, and under a microscope, if the Teflon material had gaps like that, these molecules would find their way through. So when you're thinking about selecting the right hose for an application, you need to understand what are the gases being conveyed and what are the materials that are in the core tube of the hose to understand if it's compatible or not. When we think about compatibility, it's not just with the chemical. Is it chemically compatible? You also have to understand permeability. Looking at braiding, hose braids or reinforcements can be a number of materials ranging from fabrics to different types of metallics. These reinforcements could be for pressure, they could be for kink resistance, could be to eliminate torsion or twisting of the hose, reduce volumetric expansion of the core tube, but I think most importantly, braid reinforcements add for flexibility. The ability to keep the core tube round will overcome kinking. So, to again go back to the garden hose, if you take your garden hose and you start to see it bending, and when it bends beyond the point of the minimum bend radius of the hose, it starts to flatten out and starts to oval out. So really, in a hose design, you want to keep that core tube round. If you can keep that round, it's going to be strong. The second it starts to lose its shape, it becomes vulnerable, and it can't handle the weight. Okay, so that's really what the intention of reinforcement is, to allow for flexibility. So as you can see from the picture, that's what a hose braiding would look like. The core tube's coming through. You have, in this case, it's stainless steel. You have the different carriers or different bobbins, and they move in and out of each other. So what I'd like to do is share with you a video on what this looks like. So this is a slow motion. If you look, the carriers or the bobbins are dancing in and out of each other, 2 over, 2 under, okay? This is a very controlled process. There's the angle, the tension, all of that comes into play. And as a result, the tension of the braid, the angle that it's coming down, will control what type of flexibility characteristics you have. Now we're going to look at that in real speed. This is how fast these braiders are moving. And I wanted to show you the first slide so you understood what these carriers were doing. But again, this is a very controlled process. And the result of this is you get flexibility, you get pressure capabilities, protection of the core tube. There's a lot of reasons for braid reinforcements. And so, you know, we put a lot into our design on the angles and the tension and what type of materials we're using. So now the last piece of the hose itself is going to be the cover. The cover itself can serve a number of purposes. Cleanability. You could have a wash down type application, sanitary application where they're concerned to have crevices, insulation against hot and cold media. Be able to, the ability to put a ley line on the cover, so you may have where you need to identify what is the hose material, where did it come from. Silicone or any types of rubber covers allow you to mark the hoses. But it's important to know covers by themselves do not do anything in terms of increased flexibility or increased pressure. These are just simply cosmetic. Now, there are some reasons that you would want to add covers to a hose, and there are some that will not be integral to the hose, but will, in fact, help with prolonging the life of the product. So on the left-hand side, we call this armor casing. It's a 304 stainless steel flexible conduit that gets applied to the hose to help against overbending or kinking. So in other words, if you had an issue where your hoses were kinking because of excessive bending, you could put armor casing on there. If you had where hoses were going to be, they're dragging hoses around and they're finding that the braid itself is wearing down prematurely, armor casing could be a good option for you. The one in the middle is it's a spiral guard. It's an HDPE plastic. It gets helically wound to the hose. This would be one that would be more catered towards abrasion issues, where again, where hoses are being dragged around. And the last one to the right is a fire jacket or fire sleeve. This is a fiberglass silicone mixture, and these are typically applied to hoses where there's concern of burn. So in other words, if you had any hot oils or a steam line that would stainless steel and it was exposed and associates were burning themselves, you're concerned with personnel getting injured, you can apply a cover like this to protect them or surrounding equipment. Let's take a look now at the end connections, because the end connections is a critical part of the overall hose assembly. There are a lot of different types and different standards, which make it even more confusing. And when you think about how we've really become a global economy, there are all different types of standards out there. So knowing the standards, having the right end connections on the hose is going to provide a lot of value. And what I mean by that is, if we were trying to mate up with a certain standard and the end connection wasn't integral to the hose, we'd have to use an adapter. Now, anytime you use an adapter, you've now put a potential leak joint into your system, okay, depending on what type of fitting you're using. But I think most importantly, when you think about it from a hose standpoint, hoses are typically used because of the need of flexibility. So anytime we add an adapter, we reduce the amount of flexible hose being used. So having that integral as one piece could bring a lot of value to your application and, again, prolong the life of the assembly. The last component, I know it's not a part of the hose, but we like to categorize under that as options. Now, these options could be the driving factor for selecting the right hose. For instance, tagging. Identification is becoming more and more important to understand. when you use a tag on a hose, you could be calling out what facility or what suite the hose is being used in. You could be calling out what is the hose product, what's the media being used. It could be the date of manufacture, date of replacement, the color coding can be used. There's a lot of value into having a tag on the hose, because I've been through a number of facilities where it's lost. All that data is lost. They're not sure how long we've had this hose. We're not sure where we got it from. So being able to identify that as the hoses are being installed could help you long term with understanding the application and which hose is being used for which. And then certifications, understanding that there are a number of different cert needs when you're writing a specification on a hose. Understanding what certifications are available or come standard or can be ordered could also help you with selecting the right hose for the application. So now that we've gone through the construction of a hose and the guidelines for proper hose selection, let's apply these 5 steps in an application scenario. Okay. So what we're looking at is we now have the core tube, right? We have a semiconductor customer that needs coolant transfer lines to convey floor inert. Floor inert is a heat exchanger fluid that's extremely aggressive, is hard to contain inside of a hose. The application parameters of the application is it's a 3/8 inch hose, that's the core tube. Static dissipative is the need. Internal working temperature is 350 degrees F. From a reinforcement standpoint, we need a lot of flexibility because the hose is going to have a lot of routing. Cover has to have a temperature of 180 degrees F. So what the customer is saying in this application is hose has to have some sort of insulating characteristics. Media temperature 350, cover temperature 180. Hoses also need to be color-coded. It's a clean room environment, so that's of importance. End connections, stainless steel tube adapters, pretty straightforward. Options, hose needs to be traced, date of manufacturer, equipment number, and building number. Just what we just talked about with tagging. So going through a catalog, and so we'll go through our catalog. I was able to find this product. It's the W Series hose. It looks like it in the catalog. You can see from the different features. It seems like this is a product that could have some solution for this application. So let's look a little bit deeper and see how it does. So looking at it, the hose ID is 3/8 inch. Well, W Series is available in 3/8 inch and 1/2 inch size. Static dissipative, well, good. The hose is available with a static dissipative core tube, so we're going to be good there. Internal working temperature 350. It's Teflon, so it has a range from -65 to +450 F. And I put a reference here. You're going to look when you're specifying for a hose or going through hoses. Technical data will be listed in most product pages. That's going to tell you the basics: inside, outside diameter. There's your bending, temperature ratings, working pressure, and then weight. So it's going to give you most of what you're looking for. Now, flexibility was important because of routing. So looking at it, this hose does exceptionally well because it has innovative braid technologies that allow this hose, that being a smoothbore, has a lot of flexibility. So that's going to be good for us when it comes to that routing need. Now, as far as the cover goes, now one in an insulated type design, again, 180 degrees F. Well, it has a silicone cover, and then it has an insulating wrap inside, so that looks like it's going to hit the mark. And then we see that there's a product test report. So the PTR is product test report. So a test was run to put media through this hose and then measure the insulating characteristics of it. So we now have a proof source. That's helpful as well. Clean room environment, well, the hose is available with a smooth silicone cover, so it's going to be cleanable. And then the hose is available in blue, black, red, and white. So it looks like it's going to do everything we need it to do. So end connections. Stainless steel tube adapters, well, good. Look in the catalog. Crimped on stainless steel tube adapters are readily available for the products, so no need for adapters. And then lastly, the hose is available with different tags. So there's a Perma Tag here, which is a silicone banded label. It has 5 lines of text, 25 characters per word, and available in different colors. Good. Looks like we're going to be able to do all we need to do with this hose. So I want to end with something that I started with. Okay, I like to go back to the car analogy tire if I could. Now, thinking about, there are a number of tires designed for all types of terrain. Understanding what tire would be best suited for your needs is very important. Additionally, understanding what causes early fatigue and what you can do to prolong the life. Understanding what fatigue looks like and acting upon it will also be very helpful. So, just to put this in perspective, would you drive 65 miles an hour down the freeway or the highway if you knew your tire had a blister in the sidewall? I don't. I'm much more proactive. So the question is, why don't we act that way when we were selecting the flex hoses for our applications, right? The comparison is almost identical. So my point there is, what I want to leave with you before we get into questions is, there's a lot of things that we can do up front. We have to understand the applications. We have to understand that if we don't put enough thought into selecting the right hose for the application, our entire system could be jeopardized. Once the right hose gets installed into the application, what can we do to identify areas of improvement, and what are we doing to identify where there's potentially breakdown or where the hose is wearing out? You know, if we use the car analogy, are we starting to see the treads wearing down? And then what are you going to do about it? Okay, so again, if you see a hose that looks like the integrity may be an issue, that it's a misalignment, it's kinked, you should be replacing that hose, because you never know. The tire could be fine today, but you could have a blowout tomorrow. So it's really, do you really want to make sure that you're doing all you can to examine them too? Okay.
We do have a few questions here. One is, you said something about the difference between dynamic and static bend radius. Could you say what the difference is?
Sure. That's a good question. So the difference between dynamic and static bend radius. If you look in the catalog, as I mentioned earlier, it's the technical data, you're going to see for bend radius, again, the minimal amount of bending that the hose can do before it starts to kink. There would be two ratings. There's going to be a static and a dynamic. Static is where the hose would go into an orientation and stay there. So in other words, if we had a U-like shaped setup where the hose was connected and it wasn't going to move, that would be a static application. The bend radius there would be what the measurement is between the two spaces. Now, if we took that same application now and that hose was going to do a lot of movement, so moving up and down, we would then take a more conservative approach on the bend radius, factoring in now you have material of movement. So if that hose static was a 6-inch bend radius, you may see the dynamic dynamic bend radius be more around 8 inches. But it's mainly with the movement of the hose product.
Question just came in that's interesting, and then we'll work our way back to some earlier ones. Is there permeability data for the different core tubes and common fluids?
Is there permeability data for the different types of core tubes? Mm-hmm. No. So that is a great question. We certainly must have some experts on the call here, because that is one that we see all the time. So permeability, there's a lot of variability that comes into that. So to give you some examples, if we had a hose that was 2 feet long, and then we had another hose, same materials, that was 50 feet long, put into the same application, so nitrogen or whatever it be, the 50-foot hose is going to show results of a much higher rate of permeability, even particularly over a period of time. That's because the exposed amount of hose. Now, if you took those if you took the same hose product and you put it into different types of gases or different types of pressures, cycling of pressure up and down, you're going to find out that the rate of permeability is going to be all over the place. So it's, I guess to sum it up, it's almost impossible to answer without running a test mirroring that specific application because of all the variability in there. I would say as a rule of thumb, if permeability is a concern to you, you want to start with what's the least permeable material. So you look at an all-metal hose. Now, if that all-metal hose can't give you all the other characteristics that you're looking for, because in a lot of cases there's a good, better, or best scenario. So maybe the all-metal hose is great from a permeability standpoint, but then you're looking at it and it's a dynamic application, so there's a lot of movement. You may want to look at a material that covers both. Is maybe not as good with permeation, but offers better flex fatigue, or is better against flex fatigue.
Okay. Another here is, any concerns about using static dissipative hose in an application that does not require it?
Also, good question. So static dissipative hose, is there any concerns with using a static dissipative hose versus a standard hose? The only exception is going to be a pharmaceutical type application where if you have a really sensitive media, so it's again a vaccine facility or maybe a food account where you're concerned with that product coming in contact with Teflon that has carbon added to it. You know, the leachable or extractable rate of those is just about zero, but there's a concern that it could happen. So I would say that's the only exception. Outside of that, if we're talking general industrial application, any other non-pharmaceutical application, no, because when I'm working with customers and helping them select the best hose, if there's any concern that static failure could happen, I default to a static dissipative hose.
Okay. And a related question, who should be checking hoses at our plant, and what are some indications a hose is wearing out?
So checking hoses at your plant. So, well, you certainly want to make sure you partner up with companies that have the expertise. So, you know, we certainly have a global distribution network. You have Northern California has certified people that are fully capable of doing integrity evaluations, assessments at your facility to look for, you know, improvements of misinstallation, misalignment, those types of, there's some easier ones to look at. You know, obviously if you look at a hose that's kinked or has braid wearing, you know, so for instance, if you have a stainless steel braided hose in your facility and the braids are broken, there's a potential there. You know, now the pressure containment of that hose has been jeopardized. So, you know, there's, you know, I would say kinking, braid wear, you know, where you could see where a hose looks like it's bending against its natural curvature. There's some really simple things to look for, and I think being able to leverage local resources to come out and assess it would certainly bring value to your applications.
Okay, and another question that just came in, 7P series hose says it is static dissipative. Is the polyethylene also mixed with the carbon?
Some materials, so Teflon has to have carbon added to it. The carbon in Teflon is what makes it static dissipative. So, and the reason Teflon has to have a carbon added is because it's such a wonderful insulator. So, you know, good insulators are bad when it comes to static charges. So the 7P hose is not Teflon, so the material itself is static dissipative. So the design itself gives you a static dissipative hose.
Okay. And what are typical applications where you see the wrong hose being used?
Well, that's another good one. You know, it's there are some easy ones. So you know, the ones that jump out at me, all metal hose. You know, as I mentioned earlier, with the aluminum can flex fatigue. So if you have, you know, just to give you an example, a tire press application where you have the molds coming up and down as the tires are curing, and you know, so these hoses constantly move up and down, up and down, up and down. Well, you know, if you're using an all-metal hose because you're looking for something that has compatibility with steam and is fairly flexible, that's a good choice. However, because of the dynamic application, that metal will wear out prematurely. So, yeah, it works for a certain period of time, but you're finding out when you're looking at it, you're replacing hoses more frequently than you would like. You probably want to go with an alternative material. You know, for that instance, convoluted Teflon hose, far more flexible, much better for continuous flexing back and forth, and also steam compatible. Now, to look at one that you probably wouldn't want to use in gas applications, and to go back to my example with Teflon, you know, if you had a helium or hydrogen line or concern of any permeation, Teflon's probably not the ideal choice. Gives you a lot of flex characteristics. It's smooth bore, economical, but you know, could present some issues there. I'll give you one more. like a rubber hose, push-on rubber hose, which it's great because of ease of installation, multi-purpose hose, but with water at elevated temperatures, that has a negative impact with the BUNA over a long period of time. So there's other choices out there.
Okay, more questions rolling in. I think we were wrapping up at 10:45 Pacific at the latest, so if more come in, let's transition to trying to answer additional ones at the blog, perhaps. So last one for this morning, convoluted hose, when should you use annular versus helical and vice versa?
Oh, good question. So convoluted hose, annular versus helical, when should you use one versus the other one? You know, from a performance standpoint, I don't know that there's really much of a difference. So just to remind those of you that are still trying to understand the difference of the two, reminder: helical is a continuous convolution. Again, that thread. Annular is the convolution terminates in another one. You know, you're going to find that most Teflon hoses have a helical design. The reason they have a helical design is the process of making them allows it to go into a helical design. So helical versus annular, helical provides less turbulence. So if you're putting a media through the hose, if there was an annular design where the convolution is terminated, you'd have a much higher level of turbulence. Helical also is a little bit better in terms of drainability, but I want to be careful there because, you know, if drainability is the utmost concern to you, you probably don't want to be using a convoluted hose. But again, benchmarking one versus the other one. Now, all metal hoses are typically, now there are exceptions, but are typically designed with a annular design versus a helical. Reason being is the manufacturing process of those hoses is you take a metallic tube and then you're just compressing it like an accordion, you know. So with that design, you end up getting annular convolution. So in terms of performance in your applications, I don't know that it would drive me to select one versus the other. I think it's just more of you're going to want to be more interested in the flexibility aspects of it than anything else, and using the right materials.
Great. We have about 60 seconds to wrap up, so we're making a note about additional questions. Thank you, Patrick, for all your expertise. We'll post a recording from today at norcal.swagelok.com, as with other technical briefings. To reach us, please visit the request information page at our website. It's under resources, or call our office at 510-933-6200. Thanks again, Patrick. Thanks to each of you on the line, and we will now close this technical briefing. Goodbye.